Hello, students of statics. This is Dr. Dan Baker, and in today's lecture, we are going to talk about frames and machines. Now, frames and machines are the last topic we'll cover in our equilibrium of structures module. And so we've been looking at all two-force member systems, right? All trusses we defined as two-force members. And so we're going to take a departure from that as we get into frames and machines. And actually, frames and machines we treat much more like the single rigid bodies we looked at in chapter 5 than we treat as the two-force systems that we've looked at so far here in our chapter 6, equilibrium of structures. So let's make a little table to talk about the differences between these various types of equilibrium. This is going to be a 3-column table. I'm going to make it most of the width of my page here. So talking about two-dimensional equilibrium. And then two-dimensional trusses, which we've been covering the last few videos. And then now two-dimensional frames and machines. Shift things over just a touch to get a little more balance here in my table. And so for 2D equilibrium, we had one single body. And that body was subject to multiple forces and possibly also couples. We tend to call these commonly multi-force body. Okay, one single multi-force body. In 2D trusses, we had many two-force bodies. And then for frames and machines, we're going to have multiple two-force and or multi-force bodies. Okay, the key thing here is that we need at least one, so greater than or equal to one multi-force body in order to create a frame and machine system. Of course, if we had all two-force bodies, we could treat it just like a truss. Okay, so the next row here, we're going to talk about what kind of free body diagram we create. So we created here a free body diagram of the body. For 2D trusses, we created either free body diagram of joints, or we also did a free body diagram of sections. Okay, both of these techniques, both joints and sections, only work if 100% of your system is two-force bodies. What we'll see is that if we have multi-force bodies in the system, we need to create free body diagrams in this case, because frames and machines have more than one body, free body diagrams of bodies. Okay, so this parallelism between multi-force and free body diagram of the body. Here again, multi-force free body diagram of the body. Only when we have all two-force bodies, which is true of trusses, can we do method of joints or method of sections. And then the last row of this table, let's just talk here briefly about equations and unknowns. For a single body, we know we had 3 equations. We could solve for 3 unknowns. Permit me just to abbreviation there of unknown UNK. For 2D trusses, if we did method of joints, we summed our forces at each joint. And then for frames and machines, because these act more like our single multi-force bodies, we are going to have 3 times the number of free body diagrams are going to be our number of equations. And therefore, we can solve for 3 times the free body diagram's number of unknowns. Okay, so 3 times our FBD's unknowns. Okay, so the techniques we use fundamentally in frames and machines are much more similar to what we did in chapter 5 than we have to anything we did in chapter 6. The reason they lie here in chapter 6 is that in chapter 5 we only dealt with single body systems. In chapter 6 we're dealing with multi-body systems. Okay, let's take a look at what this looks like. So if we have this stool and we want to create a system of free body diagrams, what we'll do is we will isolate each one of these pieces. Okay, this is going to be leg E, C, B. Let's draw over here the other leg. So this is going to be D, C, A. Here is that connecting member between them. Right, so this is A, B. Let's draw the seat top up here. And this is point E and point D. Now noting that there is only one single applied force in this entire system, now often we would call this a frame, mainly because it's not designed to move, it's not designed to have any motion, it's just designed to be static. But once again, both frames and machines will evaluate exactly the same way. The key point here with frames and machines is that when we created a single free body diagram, we knew that we could assume any direction we wanted for its reaction forces. Now here we're going to have reaction forces. Let me get these listed. So I'd have a normal force down here at A. So call this N sub A. I'd have another normal force pushing up here at B, N sub B. So those would be my reactions. And then I'm also going to have interaction forces that are basically happening between bodies, right? So if we have interaction forces between bodies, let's go ahead and assume here at C, I have a horizontal force Cx, a vertical force here Cy. Okay, so here is the key thing with frames and machines, the probably most important detail. And that important detail is that when I transfer these forces from C on the body over here to C on the body over here, I need to transfer them equal and opposite. Okay, so equal and opposite means that Cx on this other body needs to be going to the left because that's Cx going to the right, and then Cy needs to go down. Okay, quite honestly, that's probably one of the main challenging parts here to frames and machines. Otherwise, there are a lot of algebra. Okay, let me go ahead. I realize I put these point forces or these points here a little too low. Move those up. Sorry about that. Use your eraser. So A and B. We'll leave those normal forces down at the bottom. Actually, let's just go with, call these N1 and N2, just so we don't confuse them with the forces going on at A and B. Okay. And so now looking at AB, AB is pinned on both ends. There was nothing mentioned in this problem about the weight or mass of AB. Therefore, AB is a, hopefully you said, two-force member. So if I assume that AB is in tension, I could say that this is the force A, this here is the force B. Let's go ahead and put some sub-x's on there, AX and BX. So purely in tension. And then I get the same pulling force here in tension on A and a pulling force over here on B. All right, now I come up to E and D. Now once again, I can assume any direction I want as long as I haven't identified these yet. So let's call this dx, dy. Coming over here to D, equal and opposite. dy needs to come down, dx needs to go to the left. Let's go with EX coming back in this direction, and we'll go with going upwards here for EY. And so here we have equal and opposite EX, EY. Okay, so instead of having just one free body diagram, we now have created, in this case, 4 free body diagrams. Let's talk a little bit more about what kind of free body diagrams these are. This is a two-force member. With a two-force member, we get all of one equation, right? The only equation we end up with for a two-force member is that AX equals BX. That's it. If you sum moments, if you sum forces in the y direction, you don't get any additional information. So essentially for a two-force member, you get one equation. For a multi-force body, you end up with three equations. Okay, so here, obviously ECB has all sorts of forces applied to it. This is a multi-force. So we'll have three equations here, three equations over here for ACD, and then also ED is another multi-force member. So there are three equations available there. Okay, it's always worthwhile thinking about, do my equations match the number of my unknowns? So I have a total of 10 equations available, 3 times 3 plus 1. Now let's go through and count our number of unknowns. Okay, n1s and unknowns, there's 1, 2, 3, 4, 5, 6. Now I don't want to double count any of these. Okay, 7, 8. I already counted EX, CX, CY, 9, and 10. Okay, noting I didn't double count basically the forces that were on the connecting body. I just wanted to get an arithmetic count of equations equals unknowns. So we have 10 equations is equal to 10 unknowns. And so that gives me enough information to be able to solve this problem. Okay, so that's always a good thing to check. Just like for single bodies, you checked if you had 3 or fewer unknowns. Now we take a look here and we look at 3 equations for multi-force bodies, 2 equations fundamentally for two-force bodies, sorry, 1 equation for a two-force body, 2 equations for a concurrent force body, right? Remember that if we had a situation, say on this seat up here, that we ended up with the force coming in here, and maybe there's a couple of two-force members instead of these multi-force members attached, right? So if all these forces were intersecting at one single point, we call that a concurrent force system. It acts just like a particle, and basically with that we could sum forces in the x, sum forces in the y, so we'd have 2 equations with a concurrent force body, right? And again, we treated particles as concurrent force bodies. So one other thing I wanted to talk about in the context of frames and machines is looking at rigid versus non-rigid systems. Okay, so if we look at a rigid system, fundamentally a rigid system stays rigid when removed from its supports. So obviously to contrast that with a non-rigid system, leave a little bit of space there. I'm going to put some drawings in between. And in a non-rigid system, we end up with, it can change shape when removed from supports. You'll see in some textbooks, this is actually the definitions they end up using for frames and machines. Again, I don't get really heavily into those definitions because we treat them all generally the same way. But for a rigid system, let's say it looks like the following. So we have 3 members. Now, this may look like a truss because these 3 members are in a triangle, but you're going to see from the loading that these cannot be 2 force members. And so let's say we have 1 force applied over here on this side. Let's say that we have a couple applied here. Now let's go with a pin here on the lower left and a roller on the lower right. So we'll call this A, B, C. Now, noting that AC does turn out to be a 2-force member, and then AB and BC are both multi-force members. Okay, so you can have a mix of these 2-force and multi-force members. And so we certainly can explode this into the 3 free body diagrams and work at solving our reactions, so AX, AY, and CY. And we could also find the interaction forces at A, B, and C. Now, I think the best way to solve these problems, if they are rigid, is just to keep them rigid for one more step before you start solving for everything. That's to leave the entire triangle as a rigid body, only leaving the reaction forces. Sorry, I flipped these labels here. It doesn't technically matter for my example, but AX, AY, CY. Here's my applied forces still of F and this couple, that moment applied right here. And then basically you can solve for this one, and this one, right? AX, AY, and CY as a single rigid body, then break it into pieces and solve for the interaction forces. Okay, so if it's rigid, I'll put often easiest. And this really just gets down to like minimizing your unknowns on each free body diagram. As we saw here above, we can end up with a whole bunch of unknowns on these bodies. And so getting rid of some of those early on can help us out. And so one would be to draw your FBD of the rigid body and solve for reactions. And then 2, I'm going to say to explode. It's very non-scientific, kind of a scientific term, but break into multiple pieces, adding all of the interaction forces. So explode and find these interaction forces. So as an example of a non-rigid system, we'll actually create a system that looks very similar to our system above with just kind of one main difference. So still 2 rigid members. Let's go with a pin down here. Now we're going to label this one, give it a different name, call it point D and E, and we'll go with G. Now, in order for this system, which is non-rigid, if you removed it from that support at D and we'll put a support over here at G, what we'd see is that we could flex those arms back and forth. They're pinned at E. But in order for it to be a system that, when it's attached to its reactions, is still going to be a rigid system, right? We can't work dynamics problems yet. We need to have a pin over here at G as well. And so basically what we're doing here is that we're substituting in one additional reaction force and one fewer internal member force, okay? Now let's go ahead and add the same applied forces, so a couple and an external force. So in this situation, which is non-rigid, right? You remove it from D and G and you can bend it back and forth, rotating around point E. The only option, and this isn't like in rigid systems where you say, do one or the other. Like this is the only way you can solve these problems. So we want to, to explode into separate free body diagrams, and then kind of simultaneously solve for reactions and interaction forces. Now you also technically could have interaction couples. In this case, we have pins. So just to remind us here, as we talk about reactions, our reactions are going to happen here at G and D. Our interactions are going to happen up here at E. Okay, so just a little bit different definition, but interaction between bodies, reactions between bodies and basically the external world. All right, so if we drew these free body diagrams, they look like the following. There is our two members. Let's go ahead and add these external loads, M, F. Let's make this free body diagram official with a axis system, X and Y. We have a pin down here at D, so dx and dy. I have a pin at G, gx, gy. And then I get my interaction force up here at E. I'm going to assume to the right. So Ex will go upwards, Ey. And then this comes back to Newton's third law, right? Newton's third law tells us that for every action, we have an equal and opposite reaction. And so the reaction here between these bodies, Ey goes down, Ex goes to the left, right? Equal and opposite. And again, if I want to keep with this highlighting, here are my reaction forces, and then my interaction are up here at E. Now for this case, we have two multi-force bodies, and we have three equations of equilibrium for each one of these. So 3 plus 3 is 6, and we could go through and count the number of unknowns. I'll do it with the underline this time. So dx, 1, 2, 3, 4, 5, and 6. Okay, now each one of these bodies has 4 unknowns, and so there's no way on this problem you could solve for all of those values before you move on to the next. But you now have a system of 6 equations, 6 unknowns. Again, this is one of the cases where a matrix solution using linear algebra may become beneficial if you're not able to fairly easily do substitution and work through the equations and unknowns. The last topic I wanted to hit before moving on is looking at pulleys in machines and kind of seeing how they manifest themselves. And so let's do this with a little case study. So let's say that we have a non-moving little part of a ceiling up here, and off that ceiling is a pin. Now here's our rigid body we're going to take a look at. Okay, so there's the rigid body. Let's go ahead and put a frictionless pulley mounted to this upper left corner, another frictionless pulley here on the lower left corner. Let's say that we have one more piece of non-moving wall down here. Okay, so our cable, let's say, runs horizontal around that pulley, around this pulley, and maybe over an angle to attach to the wall. And just to give us some kind of an applied load, let's go with a couple. Okay, so we have a couple applied to this body. Let's go with point names of D, E, and F. Okay, so I have a rigid body, D, E, F. I have applied couple C. I have some frictionless pulleys at E and F, and a cable which is wrapped around those frictionless pulleys. Okay, there's two different ways I could create a free body diagram system for this body. One which takes a whole bunch of effort, and one which is a little bit more straightforward. So this is the long option. And the long option is to create free body diagrams both of the body and of each one of these pulleys. All right, so the body, let's go ahead, we had this applied couple. We have a pin at A, AX, AY. Now I have also a pin connecting the pulley at E to the body over here. So let's go with the forces on the body, horizontal and vertical, equal and opposite over here, downwards. Now I also fundamentally, as I was drawing this system, I cut away, not only away from the body, I also cut the cable, right? So if I cut the cable, I need to expose the forces that were in that cable, those tension forces. I'm going to do the same thing down here at F. So Fx, Fy, equal and opposite, Fx downwards, Fy. Tension forces, once again, cutting away the cable. Move my Fx label there. So I wrote over the top of it. And then add an angle here, T. Okay, so I have these three separate free body diagrams, a whole bunch of unknowns. But one thing you can notice, especially if we zoom into the free body diagram up here at the pulley at E, is that if I sum my forces in the X and I sum my forces in the Y, I'm fundamentally going to find that the tension forces applied are going to be exactly equal to those pin force components. Okay, so another way that we can say this in words is that we can say that pulleys transfer cable tension directly to the pin. Okay, and I should add here also, beyond just being pulleys, these are frictionless plus massless. So if there is any kind of friction at the pin, rotational friction, or if there's any kind of mass, right, that this pulley would have a weight, this justification no longer applies. Okay, so let's go from the long option to the short option. So in the short option, we're going to assume that those pin forces, or excuse me, the tension forces are going to apply right to the pin. So we still need some pin forces over here, AX and AY at A. We still have an applied couple here, C. But now at point E, I'm basically just going to draw the tension forces that are being transferred through that pin. So it looks like this. T comes down, T goes to the right. Okay, once again, you're essentially working through this other free body diagram in order to get that equality. And to do the same thing here at point F, we have a tension force going up and a tension force coming down at the same angle, right? The same angle that was here, call that angle theta. We're going to find that's the same angle here for this other tension force. So fundamentally on this problem, this T and this T would cancel, and that the only tensions you're really dealing with are those that are cutting this body away from those the ceiling and wall. And so I typically will choose this option right here, and I'm totally fine if you basically understand the justification for that rule, and then you can apply that. So really what it did is it took a frame and machine problem with multiple bodies, and in this case reduced it to one single rigid body. Now, after you end up with your free body diagrams, again, go through and solve for your equations of equilibrium. One thing that makes the graders very happy is if you label your free body diagrams. Okay, so in this case, maybe we call this A, B, and C, or you can label them according to the body. So it could be AEF and pulley at E or whatever else. But as you get down to your equations, say, hey, for free body diagram A, I'm going to sum my forces in the X equals 0, sum my forces in the Y equals 0. Then as I get to free body diagram B, I have some different equations, summing forces in the X equals 0, etc. Okay, but provide some delineation between those so that we, as we're grading, and also you, as you're reviewing problems later that you've already completed, can tell which equations come from which free body diagrams. Okay, so again, make sure that your labels are unique. Any kind of unique force or couple deserves its own unique label. All right, hopefully that was a helpful overview of frames and machines. Now you can apply all of your knowledge to solving these equilibrium systems, to solving frame and machine problems.